follow me when I do the exercise. Okay. And I've sent it on the group. There are no doubts about it. We will start with an easy exercise. We will start with exercise we will start with exercise 4.1, and then we will move on to 4.3. So, as before, we read it all together, and then we will solve this recurrence relationship on the whiteboard. And whenever you have questions again, please let me know, okay? Because this is an important part, and I want you all to really, really understand it. So, we have to consider the recurrence relationship xt is equal to 1 over 2 multiplied by x of t minus 1 plus 4 for every t bigger or equal than 1. The first thing that we notice is that this recurrence relationship, it looks exactly like the form that we've seen just earlier on the whiteboard. So this is the initial form of the recurrence relation. This exercise is asking us to compute the first 8 terms of our recurrence from x0 to x7, knowing that, the first 7, because we are given x0 is equal to 56. Then we have to solve the recurrence relation. So that means that we have to get to that final form, to the final solution that I've just explained on the slides. Then we have to give the solution of the recurrence relation with the value x0 is equal to 56 and compute the 20th term. And then they ask us, where does xt tend to? As t tends to infinity, which means becomes very large. Does this depend on the initial value x0? Okay. If everybody has written down the exercise, I'm going to write a few more details as well for myself so I can move on to the whiteboard, and we will begin. So, okay. So we are given an initial recurrence relationship that looks like this. xt is equal to 1 divided by 2 multiplied by x of t minus 1. This is x of t minus 1, okay, not to the power of, because remember when I write down to the power of, I write it like this. So this means x of t minus 1. So it's a term in our equation. Plus 4 for t bigger or equal than 1. Okay, so we have to first, knowing that x0 is equal to 56, we have to calculate the first 7 terms of our recurrence relation. We're not going to calculate the first 7 of them because we don't want to lose time with that right now. We just have to replace inside the recurrence relation the respective x values in order to calculate the next term in line. Okay, so we have x0. We can calculate x1 as 1 divided by 2, given by the equation, multiplied by the x of t minus 1. X of 1 minus 1 is x0. Therefore, I'm going to write 1 over 2 multiplied by 56 plus 4. And this should yield, this is 28 plus 4 should be 32. Next term in line x2 will be calculated exactly the same, following the same pattern. So 1 divided by 2 multiplied by x of t minus 1. This one, 2 minus 1 should be x1. Therefore, it's 32 plus 4. And this will be equal to, this is 16 plus 4, should be 20, and so on. This is how we're going to calculate all of them until x of 7. Okay, this is part A of the exercise. I'm going to write here A. Part B. Part B tells us that we have this recurrence relation and we have to solve it. So we have to give a solution for this recurrence relation. And I will point you right now to the cheat sheet I had sent you on WhatsApp as well. So in order to solve this exercise, I've told you that the first step is always going to identify the component parts of our recurrence. So we need to identify xt, xt of x of t minus 1, and bt. xt, we have it. It's right here. A, we have it. It's right here. So I'm going to write it down. A is equal to 1 over 2. X of t minus 1 exists. And then we have to identify our b. Our b variable will, our b element will be this plus 4. So this 4 right here. What type of b do we have here? It's a constant. It doesn't depend on t. Very important thing that I'm going to explain in a second why. Doesn't depend on t. Great. We have identified our a and b. What is the first step that we have to work with now? We have to identify x star of t, which will become our hypothetical solution. Looking at the table of the solutions written on the piece of paper that I've sent you on WhatsApp, if our b is constant, so it just looks like b, doesn't have any t related to it, then what solution am I going to use? I'm going to use the corresponding one, which is equal to c. Therefore, I'm going to use this c as a letter, as a theoretical solution in order to solve my equation. Because this c is constant, because c is constant, it means that all of my solutions, so all of my elements in my line, so x of t, will be equal to x of t minus 1, will be equal to any other x, and will be equal to c. So all of these elements xt will become c. What do I do now? I go ahead, because I've understood what my solution is. I've identified all of my coefficients. I go ahead, so this is the first step, and rewrite my equation according to the second step. How do I rewrite this equation? I go back into the recurrence relation, and instead of writing xt, I'm going to write c, because I have allowed my equation to gain this solution c for the first step. Therefore, I can replace inside my original recurrence all of the x terms with the solution. Therefore, I'm going to write x of t, which will become c, is going to be equal to 1 divided by 2 multiplied by x of t minus 1 is also equal to c, because c is a constant. It doesn't depend on t. Therefore, I'm going to have 1 over 2 1 divided by 2 multiplied by c, everything plus 4. And here I have to solve for c. I am going to multiply everything by a 2, so I can get rid of this fraction right here. What I'm going to obtain in the end is 2c is equal to c plus 4, which means that my c will be equal to 4. And if I'm not mistaken, c is equal to plus 8, because I multiplied by 2. Therefore, c should be also equal to 8, of course. Now that we found our c, we have to go back into our I'm sorry, guys, I lost my train of thought for a second. So now that we have solved for c and we have found our solution, we know that our solution x star of t is equal to 8. This is a very, very important thing. I'm going to highlight it in red so we don't forget about it. Oh, I can't highlight it in red. It's okay. We have to remember that our solution x of t is equal to 8, which is a very, very important thing. We'll see why later on. Now that we've done this, we can move on to the third step. The third step tells us that we have to do something about the homogeneous part of our recurrence relationship. However, the only element that we need out of our homogeneous part is our yt is equal to something called alpha, which will be a coefficient, multiplied by this constant a, this coefficient a that we've had originally in our recurrence, powered to t. So yt will be equal to alpha multiplied by a to the power of t. If I were to rewrite this with the information that I have, it means that yt should be equal to this alpha multiplied by a, which is 1 divided by 2, to the power of t, which takes me to my final step, the fourth step. In my fourth step, I'm going to have to write the final solution, considering all of the elements that I've created just now. The final solution looks like this. X of t is equal to alpha multiplied by a to the power of t. So 1 divided by 2 to the power of t. So this is my yt. Plus my solution x star of t, which is 8, plus 8. Because the final version of the solution xt theoretically looks like yt plus x star of t. This is the final version. And what I had done is simply introduce in this final version all of the elements that I do know. Like, for example, x star of t, which I have calculated one step further, and I obtained the value 8. And yt, which has always, all the time, the same formula of calculation, alpha multiplied by a to the power of t. The only thing I don't know here is my alpha. I don't know it yet. It's going to be a value that we're going to calculate later on. I do know my a. It's the one that I've taken from the recurrence relationship attached to x of t minus 1. It's 1 over 2. And this will be powered to the power of t. So the final version of my solution and the final solution of my exercise will be x of t is equal to alpha multiplied by 1 over 2 to the power of t plus 8 for every t that is bigger or equal than 1, and alpha real number. So this is how the final version looks like. It's very theoretical. Are there any questions to this point of what I had done or how I applied the algorithm or anything at all?
I have one question. It's actually really clear, everything, only like I don't know what is meant with alpha real number at the end.
Oh, it means that we have to give this condition for alpha that it can be absolutely any number in the world, be I don't know, a fraction of something or absolutely anything, except for they're called surreal numbers. So a surreal number is something, for example, that like square root of -1 that doesn't exist in our real world. It only exists in a complex mathematical world where we can take this solution out of the equation. So when I say alpha real number, it just means that it can take any value, any real value.
Okay, cool. Then I think I get it.
Okay.
Yeah, cool. And maybe one last question is at the very bottom of the whiteboard there's xt is yt plus x star t. That's like the form of our final solution. Is it mandatory to write it down in our final answer, or
you mean the theoretical?
Yeah.
No, it's not mandatory. I just wanted to write it down again so everybody is clear with why
of course
making the solution like this.
Yeah. Okay, cool.
Slides. Yeah. Okay,
cool. Thank you.
No worries. Does anybody else have any other questions? Is everything as clear for you guys as well? Okay, I'm going to take that as a yes. And I'm really, really happy if you understood this algorithm already, because it's going to make our job a lot easier when we start working with a lot more complicated B forms. So this has been exercise A and B. I'm going to copy the form, the final solution form of our xt, because we need it in order to calculate what they ask us to calculate in point C. So in part C of this exercise, they are asking us to, they're asking us to calculate the actual final version, so the final solution knowing x0 is equal to 56. That's it? 56? Yes. Okay. So what do they mean when they're asking us again to calculate the final solution, knowing that x0 is equal to 56, considering that we just calculated the final solution? I told you that this is the final version of your solution of the linear recurrence. What they actually want you to do is find the value for alpha for which this equation is correct, so that you can obtain x0 is equal to 56, and from here on, all of the terms of your recurrence relation. That's what they want you to do. They want you to rewrite this equation only with an actual value for alpha. So that's exactly what we're going to do. I'm going to make use of the fact that they gave me x0 is equal to 56, and I'm going to introduce this information into my final solution, and I'm going to find the value for my alpha. Let's see how. So I know that x0 is equal to 56 means that 56 will be equal to alpha, which I have to find out, multiplied by 1 divided by 2 to the power of t. What is t? T is my indice for my x, for my position. What position is this x on? Position 0. Therefore, 1 divided by 2 will be power to the power of my t, which is 0, plus 8. Great. 56 is equal to alpha, which I still don't know, multiplied by 1 divided by 2. Everything to the power of 0 is 1, plus 8. My alpha will therefore be 56 minus 8, which is 48. Then, the final version of my answer should be xt is equal to 48. That's the value of the alpha that I found, multiplied by 1 divided by 2 to the power of t, plus 8. And this is your actual final version of the solution. And this is how we calculate it. So in order to find the actual final version, the one where we also know alpha, we need x0. You see why? Because we need this t to be as small as possible so we can kind of get rid of the term that is sitting next to it. However, it works with x1, x4, x5 as well. It's just that what you're going to power will be of a higher power. So you're going to need to use a calculator. Luckily, I think in the exam, we can use the built-in Proctor calculator, so it shouldn't be a problem. Okay, so this has been part C, and then what is left is part D, which is a more of a theoretical exercise. I'm not going to go into too much detail with it. However, I'm going to explain to you how you can see such an exercise. So I will read it again for all of you. Where does xt tend to as t tends to infinity, which means it becomes very, very large? So when they're asking us to what tends an equation, they're asking us what would be the maximum this equation can reach depending on a condition. And our condition is that t is very, very, very large, almost infinity. So the way you think about this is imagine t takes the value of infinity and then try to calculate what this equation would be if your t had a value of infinity. So let's think about it a little bit, like logically. 1 divided by 2 is approximately 0.5. So anything of a higher power than 1 will mean that my 0.5 will go even lower and lower and lower and will be closer and closer to 0. And it makes sense. If you were to plug into your calculator 1 divided by 2 to the power of 100, then it will mean that you will have to do 0.5 to the power of 100, which will be a very, very, very small number, something so close to 0 that we will actually almost call it 0. because this number will become so close to 0, whatever we attach to it with a multiplication. So for example, this 48 multiplied by this number, which is very close to 0, will become redundant because it will also become 0. Why? Because this term of our equation here is so small that it's almost insignificant. What does this make us understand? It makes us understand that our xt is actually going to be equal to something very close to 0. So therefore, I'm going to write an approximation sign. It's approximately something very close to 0 plus 8, which is approximately 8, which takes me to my final version of the answer. If t tends to infinity, then the equation, this one, tends to 8 because 1 divided by 2 to the power of t will tend to 0. And this is your final version of the answer. Then it also asks us as a forward question, does this mean, after we have understood to what extent does this equation tend to, does this equation depend on our value of x0? And the answer is no. It doesn't depend on anything actually, because the values, all of them that are dependent on t, on our initial value, therefore, will become redundant because of this term of the equation, which will become 0. Therefore, the answer is no. Does this depend on the initial value x0? No, it does not. And that's it. And let me know, guys, now if this exercise is also clear enough. What I mean was part C, where we have calculated the alpha, and then part D, where we did a little bit of mathematical analysis. Is this clear? I'm pretty sure this is not something that you're going to have in your exam, I can guarantee, because we didn't actually study this extensively in university, so you cannot get an exercise like this. However, if you feel like you are curious about limits and tendencies, we can further discuss. If you text me on WhatsApp afterwards, I can tell you a little bit more about it. So you don't really have to worry about this exercise if you didn't understand it completely, because it's not something that's going to go into your exam. However, part C is. So if you understood this, then we're all good to go. So let me know. Yes, clear? Okay, perfect. Then let's take a 2-minute break so I can also get some water and some coffee. And when we get back, we will work exercise 4.3 because I really want you guys to understand what we did together. And after exercise 4.3, we're going to do one of them together. I'm going to ask you to do one by yourselves as well, just like we did yesterday. Okay, so 2 minutes to get a cup of coffee or something. So until 9:47.